Last time we started talking about transformations, right, and primarily the 2D transformations. So, let me recapitulate some of the points which we talked about last time, particularly dealing with the homogeneous coordinates, right. So, one of the motivations which we observed was to be able to represent the transformation in the form of a matrix, right, and have a uniform or unified representation for all the transformations, right. So, looking at the nature of the transformation, for instance, in translation and the other transformations like scaling and rotations, we wanted to combine these. One is additive, translation is additive, and rotations and scalings and other linear transformations are multiplicative, right. So, we wanted to put it in the uniform framework. For that, we introduced homogeneous coordinates, right, and the idea there was that we have these transformations like scale, rotate, reflect, shear being captured in the transformation T, right, as a matrix, and then we multiply that matrix to this X, right. Whereas, in the case of translation, when we have the offset of the translation vector given as T, then we need to add that to the point X to get the X prime, right. Now, what we do is we basically introduce homogeneous coordinates where we add an additional coordinate which is W, right. So, we have the same point now P being represented as x y w instead of x y, right. So, in turn what we observe that there could be multiple values for the same point, right. So, what are we trying to actually say here, that we take the representation of the point which was in 2D space into another space, right, with having a third dimension of W, right. So, and in fact, geometrically when we observe, we get something like this, a space where we have a representation of the point in terms of like a ray, right, in terms of a ray, right. So, we take the 2D space to a 3D space, which actually has become what we call it as projection space, right, because depending on what W I choose, I get a particular value for the point, right, which is the same point in the homogeneous coordinates, right. So, that was the geometrical interpretation. So, we basically take the representation of a point in a projective space, right. There is an interesting observation here. What happens when W becomes 0? What happens? Pardon me? What does it mean? See, when I have W is equal to 0, the point which I am talking in my Cartesian space is a point at infinity, right. So, I have a mechanism now to be able to represent even points at infinity, which I did not have otherwise in the Cartesian space, right. And these become more relevant when we actually talk about projections and perspective transformations, right, because there we will be talking about what we call it as the vanishing points. Vanishing points actually are points which are located at infinity. So, how do we represent those points, right. So, this basically facilitates us to be able to represent even the points at infinity just by giving value of W as 0, right. So, now then we actually also looked at 3D transformations, right. So, 3D transformations again in the homogeneous coordinate system can be represented through now a 4 by 4 matrix, right. So, let us see again some of these transformations which we looked at last time. For instance, scaling, right. Scaling is now a 4 by 4 matrix where the diagonal contains the various scaling factors, right, Sx, xy, sz, right. Now, we know that scaling is actually a non-rigid transformation. Non-rigid transformation meaning that the shape and the size get changed here, right. There is a distortion of shape, there is a distortion of size, particularly the size, right. The shape as such remains the same, but the size changes. When I have the non-uniform factors of scaling, then even the shape changes, right. So, these are basically non-rigid transformations because I am not able to preserve the shape. And there is an interesting thing is that when I look at, let us say, the inverse of the scaling matrix, which is represented as S, right, I can construct that inverse transformation just by taking the reciprocal of the scaling factors, right. So, the matrix consisting of this actually gives me the inverse transformation of this scaling, right, because at times we require to perform an inverse operation of scaling, right. So, there it is very easy to determine the inverse transformation, right. And some special values, like if I have the scaling factors negative, then I also have the reflection, right. Then we look at the rotation, right. So, the rotation matrix now, in fact, it is basically the same extension what we had in 2D rotation, right. 2D rotation implicitly involves the axis coming out of the plane where the rotation is taking place, right. Therefore, rotation is actually about an axis, right. So, when we look at rotation in 3D, then we consider the various axes about which we can perform the rotations and the matrices we obtain from those rotations, right. So, for instance, if I am interested in rotation about x axis, right. So, that is what it basically means, right. And in fact, you can look at something like a rotation which would have been performed in this yz plane, right, and the rotation would have been just this submatrix here, right. And remember, we have the convention of positive rotation in a right-handed coordinate system given by the orientation of the fingers when the thumb is representing the axis of rotation, right. So, we keep that convention in mind. So, now if I look at, for instance, rotation about z axis, this is what the scenario is, right. So, again I can look at this rotation something similar to as if there is a rotation in xy plane, right, which is given by this, right. So, I get rotation about z axis, right. So, if I was to do the rotation in 2D, then I just reduce this matrix cutting down this row for z and this column, right. So, basically I get a 3 by 3 matrix, right. Now, when we talk about rotation about y axis, this is the scenario, right. Again I can think this to be a rotation being performed in xz plane, right. And remember, we have this convention of positive rotation, right. Now, when I performing this rotation in xz plane, you see that the rotation is happening in this direction, right, and often we measure the angle in this direction, right. So, in effect, we are performing the rotation by the negative angle, right, and that is why this minus now has come here, right. In the earlier rotations, you had seen that the minus was here, right. This is a positive sign term. So, now there is a flip of it, because I basically I am preserving my convention of positive rotation, right, and therefore, this rotation is in effect by an angle minus phi, right. Is it okay? See, the rotation is happening now in this direction. That is what my positive rotation is, right, because then I would have the y axis acting as a thumb, right. If I were to measure the angle from x to z, right, what would have happened, which would give me the rotation there, the y axis would have acted in downward direction, right. So, I just reverse that, right. Therefore, the changes sign occurs. Okay. Next, now let us say if I am talking about rotations in general, it could be rotation about x axis, it could be rotation about y axis, or it could be rotation about z axis, right. So, class of rotation transformation, basically they are rigid transformation, because there is no change in shape or size, right. Another interesting observation is that if I have to invert my rotation, right, therefore, I am trying to find out the inverse transformation for the rotation, then all I have to do is perform a rotation by the negative angle of rotation, right, and that is easy to verify, right. And similarly, I also observe that the inverse matrix for a rotation by an angle theta is actually the transport matrix of rotation by the angle theta, right. So, therefore, when I am trying to find out the inverse of a transformation, all I have to do is just transpose that matrix, right. And in fact, that gives me that the matrix is basically an orthogonal matrix, right. So, what can you say about the determinant of this matrix? Determinant is unity, right. So, orthogonality, you know what that means, right. In fact, you can consider, let us say, a column of a matrix, right, and then you can check that orthogonality using a dot product of those column vectors, right. Okay. So, these are some properties of the transformation and the corresponding matrix of the transformation, right. Now, similarly for translation, when I am to perform the translation, so basically an object is translated to this location by an offset vector, right. Then again translation happens to be a rigid transformation, right. Translation is a rigid transformation, and the inverse of the translation matrix can be obtained just by taking the negative offset, right. So, LMN, which was the offset of translation, now if I just use minus L minus M minus N in the same matrix, it gives me the inverse of the matrix of translation using LMN as the offset, right. Okay. Again, when we see the transformation of shear, basically here we have the non-zero off diagonal terms, right, that give us the shear transformation, and shear is a non-rigid transformation. We observe a distortion in the shape, right. Now, just in a similar way as we have seen for other transformation, how we find out the inverse of this matrix. Of course, in general we need to find out the inverse as a general matrix, but for certain particular special cases we can again find out the inverse as a simple transformation in the values of the transformation, right. So, let us take an example where I consider a simple shear, right, where the object is basically sheared in x, right. Now, the x y, if I just look at the plane x y and I assume that there is no change in the z values, right, then the point x y is changed to x prime y prime, right. Now, if I see what x prime y prime becomes, right, and I let us say assume that there is this angle which is made by this line. So, I take the projection of this point on the x axis, right, and this is the angle which is made by this x prime y prime from the x axis theta, right. Then I get x prime is equal to x plus y cot theta, y prime is equal to y, and z prime is equal to z. So, there is no change in y and z values, there is only change in the x value. So, in order to have this transformation, this axis should be where? Is strongly placed. In order that I obtain this, where, so this is my coordinate axis, right, having x and y. Where should this be located? It should be actually located at the center of the object, right, because it is symmetric, right? The transformation is in a symmetric form. So, now using this as a transformation, right, I construct my matrix of transformation for shear, where I get this term of cot theta here, right. Now, for such type of a shear transformation, and I call this as shear yz because I am not changing yz. So, there could be convention saying that this is actually shear in x, or there could also be convention saying that there is no change in yz, right. So, let us say I have the convention that when there is no change in that coordinate, I call this to be h yz, there is no change in yz, right. Now, if I have to take the inverse of this, right, this is equivalent to just change the sign of the angle, right. So, once again the inverse of this is obtained just by changing the sign of the angle theta, right. But in general, if I have a shear and mix of shear, then I may not be able to do this direct substitution of sign or of a value, right. So, then I may have to do a inverse of a matrix as I would do for a general matrix, right. Now, just the way we had seen composition of transformation in 2D, right, the same concept extends here, right. Now, let us say I have a sequence of transformations given as T1, T2 and T3, right. There could be more. Let us say I just say I have only these 3 transformations to perform. Then the transformed value x prime is basically T1 applied to x, right, and whatever I obtain, I apply T2 on it, and then whatever I obtain, I apply T3 on it, right. This I can write as simple multiplication of T1, T2 and T3 because I have law of associativity, right. So, I can just write like multiplication of matrices T1, T2, T3 to x, right. So, in a let us say some sort of a pipeline architecture, I can think this to be x given as an input, right, and I have these pipeline units where this unit contains a transformation T1, then the result goes to the other unit where I apply the transformation T2, then the result goes to the other unit when I apply the transformation T3 and I obtain the result x prime, right. Now, alternatively, so now what is happening here? Let us say if I have an object represented by some 100 points or even more, thousands of points, right. So, what I am doing? I am taking point by point, applying these matrices to this point in this pipeline fashion, right, where each unit is actually a transformation, right. Now, there is probably a problem in this formulation in terms of computation I am performing, right. So, alternatively what I can do is actually combine all these transformations, right, just by concatenating these matrices of transformation, right, and I obtain let us say the final transformation which is the concatenated form of all the transformation as T, right, and I just apply that T to the given point x, right. So, now this pipeline is actually now changed to a structure like this where I have an input x and the pipeline unit contains the concatenated or the multiplied transformations T1, T2, T3, right, and I obtain x prime, right. So, here once I have done this multiplications of matrices, right, then I just need to apply one single matrix to all the points, right. So, which is computationally beneficial. Now, again the way we had seen in 2D composition of transformations, right, can also be illustrated in 3D. If I let us say take an example where I have to perform rotation about a fixed point, right. Normally we have seen the point about which the rotation is happening is the origin, right. So, now let us say I want the rotation to happen about a fixed point which is not the origin, right. So, let us say this point is the center of the object, this cuboid, right, and I have to perform rotation about the z axis. So, I am again considering the rotations to be about one of the coordinate axes x, y, z, right. So, if I have to do this, then I just have to make this point to be the origin, right, and in order that I do this, I need a translation. So, once I do the translation of this point C to the origin here, and then I perform my regular rotation, right, and then I take this point back to the point where it was, right, then I am done. So, that is what it is done here. We have the three transformations, one translation which is taking the offset which brings this C to the origin, right. Therefore, I have the offset given by minus C, rotation by angle theta, and then I again translate it back, right. So, now let us say I move on to a slightly more complex scenario, where I would like to have the rotation about an arbitrary axis, right. So far we have seen rotation about the coordinate axis, right. Let us say I want to perform rotation about an arbitrary axis, right. So, how would I do it? See, remember that since we know the rotation about the coordinate axis, we need to map the problem to one of the coordinate axis, right. So, which requires
First we take the axis to pass through origin and rotate it to align with one of the axis, then rotate and reverse.
Yeah. So, the basic thing is that I need to align that axis, the arbitrary axis, to one of the coordinate axis, right. Then I can perform the regular rotation, and then I do the necessary inverse transformation to put that axis back, right. That is the basic idea. So, let us try to see this. So, here I am given basically the axis by a point P0. So, the axis is passing from a point P0 given as x0, y0, z0, right, and its direction cosines Cx, Cy, Cz, right. So, these are basically just the direction vector of the axis, right, and I want to rotate about this axis by an angle delta, right. So, this is the statement of the problem, right. So, so here there is a small illustration where a rotation is basically being performed about an axis given by this red line, right, and you get a rotated kettle like this. So, now what I can actually do is, first of all, I can make this point the origin, right. That is the first thing I can do, that is easy. So, I just need to make this point origin, which requires basically a translation, right, translation by minus x0, minus y0, minus z0, right. So, what I have obtained now, this axis here passing through O, right, and specified by this unit vector OP, right, where the direction of this unit vector coincides with what I have here from the direction cosines of the axis, right. So, now if I have to rotate about this arbitrary axis OP, we said that we would like to basically align this to one of the axes, right, and let us say I choose this to be the z axis, right. So, I want to align this OP vector to z axis, right. So, how can I do that? Will that give you the alignment? First of all, try to identify what transformations will be required to do this.
So, rotate the line about the y axis and then about the x axis.
Okay, so what you are saying is that rotations are required, right. So, now what we do is we perform rotations. So, let us say, so what I am interested in is aligning this line to z axis, right. So, as a first step what I do is I get this line, right, in xz plane, right. I get this line in xz plane, which basically means I rotate about x axis, right. So, if I have to do this rotation, let us try to see what are the values of angles by which we have to do the rotation, right, so that we can form our matrix. So, here it is. Now, if you see this line in the yz plane, right, you would find this line being just sort of a projection of this onto the yz plane, right, given by, let us say, d. D is the length of this line, right. And now, if I perform the rotation of this line by the angle alpha, right, the angle can be measured in this plane now. So, if I perform a rotation of this line by an angle alpha about x axis, I would put this in the xz plane. Is this clear? Right. So, now when I am performing the rotation by the angle alpha, the alpha basically can be computed through here in the yz plane, right, because I have this as Cz and this as Cy, right, and this is d. Okay. So, cos alpha is actually Cz over d and sin alpha is Cy over d, and these are the terms I need for performing a rotation. I do not actually have to explicitly compute the angle. All I need to do is get the relevant terms which I require in the rotation matrix, right. So, I get cos alpha and sin alpha from here, fine. So, now as a consequence, this axis, this OP has actually come on xz plane, right. Now, another rotation of that about y axis would give me the necessary alignment, right. So, let us see that. So, now what I have done is, this is the axis now in the xz plane, right. Remember, it is a unit vector. So, that is why I have the length given as 1, right. Now, this side is nothing but d, right, because when I perform a rotation about x axis, if you go back here, this d will actually come on the z axis, right, fine. So, I have this distance given as d, right, Now, if I perform the rotation about y by an angle beta, right, I will align this to the z axis. Right. Now, again we compute the terms which are necessary for the computation of the rotation matrix, which are cos beta and sin beta. So, cos beta is nothing but d and sin beta is nothing but Cx, right. So, I have basically obtained all the necessary terms which I require to perform these rotations, right. So, once I have done the alignment to the z axis, then I can do rotation about z axis, which I know what transformation to use it, right. And then I do the necessary inverse operations, right, to put the axis back. Is it clear? So, the whole pipeline of transformation would basically look like something like this, right. I have first the translation, then I have the rotation about x by an angle alpha, then I have the rotation about y minus beta, well again to keep our convention in place, right. Then I have the rotation about z axis, that is what I require to do the rotation by an angle delta, right, and then I just do the inverse of these. So, inverse of r y minus beta is r y beta, inverse of r x alpha is r x minus alpha, and the inverse of t minus p naught is t p naught, right. So, this gives me the entire chain of transformations which I need, right, and after multiplying these matrices I get one single matrix, right. So, I can do now rotation about any arbitrary axis, which is very relevant and useful, right, because you would like to have rotations about a certain axis in space and not necessarily the coordinate axis, right. Okay. So, now again we look at the general transformations in 3D, basically captured by a 4 by 4 general transformation matrix, right, where I can see certain elements of different variety of transformations we obtain. So, for instance, this part gives me the translation, this part gives me the linear transformation, right, where the diagonal gives me the scaling and off diagonal gives me the shearing, right, and all these together may also give me rotation, right. This particular element gives me the global scaling, right. Remember, we have seen that this actually gives us the global scaling of the object or a scene, and these values in the last column basically are the projective terms, right, and that we will see more in detail when we talk about the various types of projections, right. So, this part of the matrix where we have linear transformation and the translation combined gives us a fine transformation, right. Okay. So, now after having seen these transformations, particularly in the context of geometrical alterations, right, geometrical changes which happen to the object, we also have this set of transformations which are relevant in terms of viewing, right. These transformations what we have seen are basically be used when I have to change the shape of the object, right, or move the object somewhere, right. But I also have transformations in a very similar framework where I can apply the transformations for performing the viewing operation, right. So, now let us try to see what we mean by viewing in general, right. So, I am basically trying to tell you what do we mean by three-dimensional viewing, right, and then we will see the various viewing transformation in the context of 3D viewing, right. 2D viewing is simple, right. 2D viewing is saying that I have a two-dimensional scene, right, and I want to view that scene, let us say, in a given display. So, it basically requires a window to window map, right, one rectangular space to another rectangular space, nothing more than that, right. Whereas, when I have a three-dimensional viewing, it is more involving, right. So, let us try to see these. So, what do I basically mean by 3D viewing? 3D viewing is something what we also perform, right. We have the idea of what the three-dimensional scene is, and there is a two-dimensional image which gets formed in our visual system, right. So, the analogy is similar. Now, let us say I have a line AB. So, it could be just not a line, but any object or any part of the scene, and which is being viewed from some point here, right, and I have what we call it as the projection plane, where I would like to see this line as an image onto this plane, right. So, this is projection plane or a viewing plane or an image plane, right. So, when we are looking at from this center of projection, so center of projection is nothing but where if I see the rays coming from the scene or the object, and in this case the line, right. So, they tend to meet at some point, right, which is the center of projection, and for the practical reasons we use these center of projection as the viewer, right, or the camera, right. So, now what we have is these projectors coming from the 3D scene, passing through the center of projection, right, and as a result I get an image here A prime B prime, right. Now, so these projectors which we have in this scenario, they are the projectors which meet at a point and they are not parallel to each other, right. So, the type of projection we get is a perspective transformation or a perspective projection, right. So, what we observe here is that the projectors are not parallel to each other. We will see more in details about the properties of perspective transformation as we go, but here the point which is to be noted, that the projectors which are basically the rays coming from the 3D scene, right, are not parallel, right. Now, I change this to a scenario where I have these projectors parallel, right, these projectors are parallel now, right. Then the resulting projection what I get onto this projection plane is parallel projection, right. So, here and if I now see where will these projectors meet. They will actually meet at infinity, right. So, the center of projection now has gone to infinity, right. So, you have definitely observed these projections in earlier in your engineering drawing or somewhere, right. And one of the very commonly used projection is the orthographic projection, which is actually a parallel projection, right. It is more restricted parallel projection. So, here what we have is, let us say if I have an object like this, then I consider my projection plane as a plane perpendicular to one of the coordinate axes or parallel to one of the principal planes. These are also called as principal planes, which are formed by the two coordinate axes, right. So, I consider a projection plane, let us say perpendicular to y axis, then I get a projection which we refer to as the top view, right. It is basically viewing from the top, and similarly we have the side view and the front view, right. So, these are nothing but parallel projections. You observe that these projectors, right, they are parallel, right. Now, so while viewing 3D using orthographic projection, we note that it may require multiple views to be able to see the three dimensionality of the object, right. So, I require, let us say, planes like x is equal to 0 or y is equal to 0 or z is equal to 0, which generate number of views where I can view the three dimensional object, right. And we also know that using orthographic projection, size and shape does not change, right. So, the true lengths are preserved, right. Now, if I have to perform this orthographic projection, let us say, right, one thing which we want is, we want these projections also like transformation matrix, right. So, that we can use these as transformations just the way we had looked at the geometrical transformation by multiplying by some matrix, right. So, now if I have to perform these orthographic projection, and let us say I consider one of the examples where I take the orthographic projection on z is equal to 0 plane, right. Then what it means in terms of the matrix which I would require is this, where I have the third column all entries to be 0, right. Similarly, if I have to take a orthographic projection for y is equal to 0 plane, then I will have this second column all entries 0, and so on. Similarly, for x is equal to 0 plane, right. So, I can construct a matrix corresponding to the orthographic projection onto different planes, right. Now, the problem which we observe here is that either it requires multiple views or we are not able to see the 3D aspect of an object, right. Now, let us say I am interested in parallel projection, but projections which will give me some more idea about three dimensional aspects of the object, right. So, these also you must have done, some of them at least. Isometric, So, in fact, there is a class of projections which we call it as axonometric, right, where what is done is that you have an additional rotation or translation or both, and then you perform the projection on z is equal to 0 plane, right. So, by combining some transformations like rotation and translation, before you perform the standard orthographic projection, it can actually render the three-dimensional aspects of an object, right. So, what we are trying to say is that, now remember that a projection actually can lead to certain changes in the ratios of the lengths, right. In the case of orthographic projection, everything was preserved, right. So, here what may happen is, due to these transformation, there could be distortions, or what we also call it as the foreshortening in each of the dimensions, right. So, in order to see that, let us say I construct this matrix T, which is a combination of rotation and or translation and a projection on z is equal to 0, right. So, this T is actually a combination of these transformations, right. And now, what I am saying is that the transformation actually can give me certain foreshortening, right. Now, in order to observe these foreshortening, or in order to compute these foreshortening, what I have is a unit vector in x, a unit vector in y, and a unit vector in z, right. So, 1 0 0 is the unit vector in x, and let us say I am saying that it starts from origin, right. So, I can have this in the homogeneous coordinates 1 0 0 1, and similarly this is my unit vector in y, and this is my unit vector in z, right. So, this is what I mean here by saying u, okay. And then I apply this T, which I had constructed, right. Now, the result would give me some entries where the last column is going to be 0, right, because I am taking projection on z is equal to 0 plane, right. So, that particular column is going to be 0, right, and there will be some terms here, right. Now, what is happening is, so you can also look at it as an individual transformation. I have put these in the form which looks like a matrix, but what we are saying is that take this particular unit vector, perform this transformation T on it, you will get this, right. Similarly, you take this unit vector, you will get this, right. So, these are the corresponding transformed unit vectors, right, with these entries, which in turn gives me the idea about the foreshortening in each of the directions, right. What do I mean by foreshortening? Basically, what is the distortion which has happened in each dimension or in each direction, right. So, if I have the unit vector 1 0 0 transformed to, let us say, x x y x, right. So, suffix x is basically referring to the unit vector in x direction, right. Then the foreshortening or the scaling or the distortion which has happened is given just by this, which I call it as f x. So, it is foreshortening in x, right. So, similarly, this is what I get as the change in unit vector in y, right, which I can compute as foreshortening in y, and similarly foreshortening in z, right. So, now once I see that the addition of rotation translation are basically giving me different foreshortenings, right. Now, I can characterize these foreshortening to be able to define different types of axonometric transformation, right. So, what I mean here is that basically I can define three types of axonometric projections: a trimetric transformation where no foreshortening is the same, that means f x and f y and f z, they are different. Similarly, diametric transformation where two foreshortenings are the same, and the isometric transformations where all foreshortenings are the same, right. So, you are familiar with isometric. So, let me give you the pictorial representation here. So, see, this is isometric where I have f x is equal to f y is equal to f z. So, all the foreshortenings are the same, right. In diametric, I have two of the foreshortenings same. So, I had basically taken a unit cube, right, and I transformed them using these projections, these transformations. So, here basically I have f y is equal to f z, and here I have all of them different, which I call it as trimetric, right. So, what we have is basically combination of rotation translation added to the orthographic projection, where we can have the 3D viewing containing the three-dimensional aspect in it, right. And depending on the type of foreshortening we obtain, we have isometric, diametric or trimetric transformation, right. So, next time we will proceed further from here and talk more about 3D viewing. Thank you.